like to introduce Micah. So Micah was a PhD at CMU, and his work focuses on distributed perception planning and multi-robot exploration, particularly with aerial robots. And he's currently a postdoc at the NASA Jet Propulsion Laboratory. And quite recently, he competed in the Subterranean DARPA Challenge, which you probably saw on Twitter. And I hope that he and his CoSTAR's team have a lot of insights to share with us. And Micah, whenever you're ready, take it away.
Okay. Well, see if I can bring up my screen share in a second. Okay, can you all see?
Yeah.
One moment.
Yes.
There we go. Okay, the video playing. I'll take that as a yes.
Yes.
Okay,
yes.
awesome.
Yeah,
okay.
so it's playing.
I'll get started then. So hello, Talking Robotics. I'm Micah Corah, and today I would like to talk to you about teams of robots that plan to observe and explore unknown environments. And more broadly, this refers to active perception problems in robotics. I will start off by discussing work on perception planning from my time as a PhD student at CMU. And I'll follow up with a discussion of my time competing in the DARPA Subterranean Challenge with Team CoSTAR while a postdoc at the NASA Jet Propulsion Laboratory. Active perception and active sensing are relevant to an extremely wide variety of robotics problems and application domains. In this talk, I will focus primarily on problems related to exploring, or you could say autonomously mapping, unknown environments. And in the case of the DARPA Subterranean Challenge, we're interested in searching those environments for a variety of different objects as well. I will also discuss target tracking problems, where robots track some number of targets, say cars, people, or wildlife. And then if the targets are stationary, we're talking about localization instead of tracking, and the same methods apply. More broadly, active perception and sensing become relevant whenever we want a robot to take actions to observe an object, operate in an unknown environment, estimate some unknown parameter, or even manipulate an unknown object, which I did in a little bit in my prior work. So why should we care about active perception problems? One application that I will focus on in this talk is urban search and rescue. In this domain, robots can provide valuable situational awareness to first responders, just by producing maps of an environment, assessing hazards, and locating survivors. Subterranean search and rescue is also the subject of the DARPA Subterranean Challenge, which I've been involved with over the past year. Aerial robots and perception tasks are also becoming increasingly prominent in rescue efforts and at the same time increasing in scope. After the recent Surfside condo collapse in June 2021, rescuers flew more than 300 drone missions through the duration of the response. Many of these flights focused on producing detailed maps of the environment to show how it was changing from one day to another. However, the scope also increased to include locating, inspecting, and even retrieving objects in the structure and rubble. Examples from the response include searching for survivors, reading license plates to identify residents, searching for pets, and documenting the presence of belongings in the rubble. So now that we know why active perception is important, this brings us to the first part of this talk, which will focus on planning for active perception tasks. One problem I would like to focus on is how to plan to rapidly explore an unknown environment. At a high level, I'm interested in two aspects of this problem. First, we can design robots that explore quickly on their own. And here on the left, I have included an example from some of my work in collaboration with Kshitij Goel at CMU. Additionally, increasingly large teams of robots can explore an environment more quickly if they are able to cooperate effectively. And this talk will cover both of these aspects of rapid exploration, specifically how to design planners that enable individuals to explore rapidly, and how to augment the resulting single robot planners with methods for multi-robot coordination with provably optimal suboptimality guarantees. So let's start by discussing single robot active perception problems. The methods I will discuss today are based on receding horizon planners, which produce fixed finite horizon trajectories that consist of sequences of concatenated motion primitives. These planners all optimize trajectories to maximize some reward, such as the notion of information gain or coverage of unknown space for observations or views along the planning horizon, as I have illustrated here. Additionally, in exploration problems, robots will obtain a reward for reducing distance to what I call informative views, and this will mimic methods for frontier-based exploration. Now, although there are a number of methods for solving informative path planning problems, such as these, we take a sampling-based optimization approach and apply Monte Carlo tree search throughout this work. So then by maximizing the amount of unknown space the robot will observe, we can obtain interesting and dynamic maneuvers, and this is something I find quite exciting. So here we see a robot executing sort of a spiraling motion to quickly and safely cover the unknown space while also planning to remain in the known free space. So one of the first steps to obtaining behaviors like what I have shown in the previous slides is to select an objective for the perception task. For example, you may be interested in observing volumes of unknown space, inspecting surfaces, or some combination of those two goals. And you may choose to weight cells in the map differently depending on the goal of your perception task. However, objective design can be challenging even once we have a clearly defined goal, because observations of unknown environments are highly uncertain, and because the distribution over environments itself can be poorly defined or difficult to sample. Moving on, one example of a perception objective, and one of the simplest and most common, is what I like to call optimistic volumetric coverage. With optimistic coverage, robots are awarded according to the volume of unknown space covered by their hypothetical future observations, assuming optimistically that all of that unknown space is empty, which produces the maximum possible reward for a set of camera views. So that's to say there isn't anything obscuring my view. So changing tracks just a little bit, information-based objectives, so-called information theoretic objectives, are based on different forms of mutual information. And mutual information characterizes how much information an observation of one random variable will provide about another. And as written here, the mutual information describes the expected reduction in uncertainty of the random variable x, which represents the map of the environment, after obtaining the robot's observations y1 to yn. So you might wonder how similar is information gain to, say, another notion of coverage. Now, what is great about information theoretic objectives is that we are often able to evaluate mutual information for individual range observations in closed form, such as from a LiDAR sensor or a depth camera. Specifically, we can do so for discretized environments with independent occupancy probabilities, like occupancy grids, whereas in octomaps, and with additive noise, typically Gaussian noise. However, accurately evaluating mutual information for multiple range observations, so multiple beams, or multiple camera views for multiple robots is much more challenging. To address challenges for information-based methods, we can start by characterizing both coverage and information-based methods in terms of expected weighted coverage. Here, consider the volume of unknown space the robot observes from a given camera view, and for a distribution over the possible realizations of the unknown space in the environment, like I've shown here. Note that in each case, the robot sees a different amount of unknown space due to the occupied cells that it observes. An exciting result from my work on this topic is that mutual information without noise fits the form of expected coverage. In other words, this special case of mutual information is a kind of coverage objective, and this realization both enables efficient, exact, or approximate evaluation of mutual information and is important to the analysis of the distributed multi-robot planner, which I'll discuss later. We can also think about how to optimize and design trajectories for exploration at high speeds. As I've already mentioned, we take a motion primitive approach, which means that we will be optimizing sequences of more or less predefined trajectory components, so 1, 2, 3, and so on. Now, I would like you to step back a bit and consider the different kinds of steady state behaviors that can occur while exploring an environment. First, a robot may move along, that is parallel to a frontier, in which case the robot plans to move through known free space while observing the unknown space. And then the speed is constrained only by the platform and design limits. However, if the robot moves toward a frontier, it may encounter obstacles that are just past the maximum range of the depth sensor, and then the maximum speed is generally constrained by the robot stopping time. So when we tested this planner in open spaces, the robot exhibited rapid spiraling motions like you can see on the left and in the plot below. And again, this is moving in parallel to the frontier, and it's able to do so then at higher speeds. Then when you put the robot in cluttered environments, the robot explored at lower speeds using those motions toward the frontiers, and generally with a more varied mix of primitives. So as a result, we're able to explore the open space more quickly on the right, and are able to still cover the environment with the same planner, but at a lower speed in the cluttered environment. So with that, let's talk about how to extend these techniques to multi-robot settings. Now, I will continue to talk about receding horizon planning problems, but now the robots will employ distributed planners to jointly optimize trajectories to maximize a collective perception reward for either tracking targets or exploring an environment. However, before we discuss distributed perception planning, I would like to briefly introduce the problem of distributed perception. In order to cooperate effectively, robots may require locally or globally consistent environment models or other sorts of shared information. Maintaining such models may invoke expensive communication costs, and one way to reduce these costs is to use compact representations of the robot's observations, such as in the Gaussian mixture mapping approach shown here. Still, sharing information can be a luxury, and the robots we deployed in the Subterranean challenge generally had much less access to shared information than what I'm showing here. So now let's get back to multi-robot planning. One way to solve receding horizon sensing problems is by sequential gradient planning, or what's called submodular maximization. With these greedy planners, each robot maximizes the collective perception reward for itself with access to the previous robot's decisions, each optimizing its trajectories with one of the single robot planners we discussed earlier. Now, although this can guarantee solutions within half of optimal, and often actually performs much better, a major weakness of this approach is that the planning duration is always at least proportional to the number of robots in the team. So this planning duration that increases with the number of robots is a major downside to sequential planning approaches, and as this conflicts with our desire to replan frequently while exploring an environment or tracking targets. And for distributed implementations, the accumulation of latency in communication alone may make sequential planners intractable for large teams of robots, let alone the time to solve the perception planning single robot subproblems. One solution to this issue in the growth in planning time is an efficient approximation of greedy planning, which I call randomized sequential partitions, or RSP. Let's talk about that briefly. When planning via RSP, robots assign themselves randomly to one of n different groups, illustrated here with the 4 different colors. Then robots in the same group plan in parallel instead of in sequence. And we then have one sequential step for each group instead of having all the robots plan in sequence. So instead of one step per robot, robots assign themselves to one of the fixed number of steps randomly. When we go to analyze RSP planning, the suboptimality then depends on a notion of the maximum redundancy between robots' observations for robots planning in parallel, as illustrated here with the intersection of 2 observations with an area coverage reward. So we're able to obtain bounds on this inter-robot redundancy on a wide variety of active perception problems. And when we're able to do so, we're subsequently able to provide suboptimality guarantees for RSP, which approach the original bound of 1/2 with 1 over n times the n being the number of steps. Our results are applicable to a wide variety of, for all sensor coverage problems, including the exploration objective that I talked about earlier, that weighted expected coverage. And we're also developed similar results for target tracking with mutual information objectives and independent targets, as I illustrated on the top right. With that, I'd like to move on to discuss the DARPA Subterranean Challenge and the incredible robots that we and all the other teams deployed throughout the competition. For a bit of quick background, the Subterranean Challenge involves exploration of a mix of subterranean domains, such as caves, tunnels, or by that I mean mines, and urban structures. While doing so, teams score points for accurately identifying and locating artifacts that are generally representative of search and rescue scenarios, such as survivors, gas leaks, helmets, and fire extinguishers. I competed in the finals of the DARPA Subterranean Challenge just a few weeks ago with Team CoSTAR, which is a collaboration between JPL, Caltech, MIT, KAIST, and LTU. And I believe we had over 40 people at the competition in person. We deployed a heterogeneous team of aerial, ground, wheeled, and legged robots. The wheeled Huskies and legged spot robots generally formed the backbone of our team. These robots were also supported by a number of drones shown on the upper right. These robots were equipped with extensive sensor payloads including LiDAR, RGB cameras, thermal cameras, microphones, sensors for CO2 gas, and more. Additionally, the robots generally communicated with the operator via mesh networks, and many were able to drop additional radios in order to maintain connectivity deep within the competition course. My own involvement with the team started fairly recently, last December. This also meant starting a postdoc in the middle of the coronavirus pandemic, which is a whole other story. My responsibilities were varied, but generally spanned drone systems, coverage planning for drones, drone autonomy and mission design, and also some work on communication systems. One fun little project was this comm roller I have shown on the left, which is actually just one of our comm nodes stuffed inside a regular foam roller, like you might use to relieve stress in your muscles after a particularly intensive workout. While the robots were able to deploy communication nodes on their own, locations weren't always ideal, and any issues with one of the nodes nearest the operator could cause problems for the rest of the network. So this comm roller actually turned out to be pretty useful, as it gave the pit crew another chance to deploy communication nodes near the base station if there were issues with one of the route nodes. Now, after all that hard work from everyone on the team, we ended up scoring 13 points and placing 5th overall. However, I think we generally agreed that result really was not that bad, so we're only 1 place behind CMU. Also, the competition was actually a much wilder ride. If you look back at the 2 preliminary runs, we managed to go from being tied for last place with 1 point to first with a 3-point lead. And that space in between those 2 days represents a huge effort by our team to fix bugs in our system and to adapt to an environment that did not quite fit our expectations. Now, I'd like to talk a little about some of the surprises and lessons learned from the challenge. Go to the other monitor to start the video. As a drone person, one huge shock came with this incident involving Australia's Team 0 Data 61. Here, a relatively large drone takes off from a marsupial rover, which is quickly downed by a piece of flying debris. And this was particularly painful to watch because this event occurred in actually one of the few parts of the environment which was open enough for effective drone deployments. And one of the only such locations we'd identified after the first preliminary run. There we go. So in a sense, this robot was actually downed in its own home. Now, some of you may have seen this video where one of the robots flew down through the entrance to the course, which was generally much narrower than what we had planned for, and then crashes at the first junction where the environment splits off 3 ways. And it turns out that our robots were generally able to accurately classify our drone as traversable terrain, as you can see here. Although a few moments later, one of the robots actually has trouble navigating over it, but that's a whole other story. Oh no. You have a problem with this video. Let's see if I can get it to load. I think they removed and re-uploaded some of those videos, so this one must not be here anymore. So if this video were here, you would see one of CMU's robots navigating a bit of a hill in one of the portions of the environment that actually had a limestone mine, or used the limestone mine where the competition was in. And it navigates up a ramp, and then it moves around a little bit. And when it starts to go down, it tries to follow a different route. And after getting a little ways, it turns back and forth, and the slope is actually much steeper than what it can navigate on. And it rolls down a very, very tall hill, landing on its side. So this is the more serious discussion of terrain classification. Oh no. Do I still have internet access? Can anyone hear me?
No,
yes.
We are hearing you, yes.
Okay. I had a warning earlier that my service might be out, and I just got a text that service was restored. This video still isn't. Okay, this video still isn't here. Okay. Anyways, this is the more serious discussion of terrain classification, which was a huge challenge for us and other teams in the competition. And in general, in mines and caves, it can be difficult to determine just how risky it is to navigate a certain slope or rubble pile, and that only gets harder in the presence of mud and water. And we encountered scenarios much like the one shown here while field testing our robots this summer. Okay, there we go. That's better. So our system did not take advantage of much direct communication and coordination between robots. This did not pose much of a problem during most of our field testing before the competition, which was primarily in more open environments. In fact, we ran a number of field tests in a nearby limestone mine, much like the competition site, except when we arrived at the Meg cavern, another very large limestone mine, it turned out that DARPA had built a much narrower course inside that larger environment. So in this narrower competition environment, we encountered much more conflict and crowding between robots than in our previous field tests. And we actually decided to reduce the number of robots we would deploy after the first round, as we had not developed robust methods to reassign, reroute, or otherwise deconflict robots operating in close proximity. So now I'd like to briefly talk about some of these challenges and for deploying multi-robot teams in subterranean environments, and also look to the future of what these systems may look like. So the first challenge I would like to focus on is reliability. Even though the top teams were generally quite successful at covering the environment and detecting artifacts, robots deployed in the sub-challenge finals experienced partial and catastrophic failures in an order of maybe once every 10 hours. Maturing these systems will likely require deployment of robots that fail instead at rates of once every 100 or 1,000 hours, and a shift toward a regime much like what we see now for autonomous cars. It is also worth noting that the aerial robots we and other teams deployed were often large and heavy enough to be only barely suitable for the narrow environment in the finals. And although this mismatch was partly due to some misalignment in expectations, the size of the aerial robots was primarily driven by need to carry heavy payloads consisting of LiDAR, cameras, radios, computation, as well as large enough batteries to obtain significant flight times and coverage. aerial robots will be able to navigate more reliably in confined environments like we saw in the finals, once they're small enough that they don't suck small objects into their rotors and can fit through narrow passages more easily. Next, the Subterranean Challenge gave me a new appreciation for communication-aware planning. The need to reason about communication and connectivity turned out to be quite pervasive and critical. This ranges from classical problems like modeling communication and connectivity to deciding when and how to disconnect from and reconnect to the communication network. And beyond that, being able to make decisions with an awareness of connectivity, such as whether to climb a flight of stairs with it, given the risk involved if the robot is unable to communicate with the human operator. Last, the confined environment of the finals led to frequent interactions and conflicts between robots. And in this regime, we could expect to benefit significantly from more inter-robot communication and coordination. As the multi-robot systems mature, I think we can expect more emphasis on field testing and hardening these subsystems involving local communication, such for sharing local maps and distributed planning. So with that concludes my talk, and we can move on to the next phase.
Okay, thank you, Michael. It was a wonderful, wonderful presentation, and that video of the poor robot getting hit by debris was absolutely heartbreaking.
Yeah, it was.
I felt
like,
over.
After that, like the first day, like you come back and get all the data, and then you look at the map and you try to identify all the different areas. And like, since our robots generally weren't able to fly in the hallways, we spent a lot of time looking for like, well, are there any large spaces that we could possibly fly in if we or other teams could get our robots there? That was the first one we identified. It's got a very tall ceiling. They actually had like tarps up to separate it from the surrounding limestone mine.
Yeah.
And then we saw the robot go in there and it took off. And then it sucked in that, I don't know if it was a poster or like a piece of foam, and it was so painful to see.
But maybe there are some lessons also to take from that, right?
Yeah. So that robot was like a very large octa rotor. Like it fit in that environment, but like when something like that takes off, it moves a lot of air. Like we flew a robot that at one point that was around a similar size, maybe a bit larger, like that moved like large foam mats or a mattress. Like, so it's not surprising that it would suck up a small object, and it's very large for even what was still a confined environment.
Yeah. So now we open the floor to Q&A. So if you have questions you like to ask Micah, please just unmute yourself or raise your hand if you want, or write down in the chat if you prefer.
Should I bring up chat? Or?
Don't worry.
Okay.
Yeah. So the first one is always the hardest. So I have several questions.
Okay.
So in these rescue scenarios that you showed, I can imagine that the scenario itself is quite dynamic, in a sense that structural changes to the environment might happen, for example, in a collapsed building or in a cave that might collapse at any point. So my question is, how does that dynamics in the environment itself affect the exploration objectives that you talked about in the first part of your talk?
Okay. So I guess it depends on how and when the environment changes. So like for the purpose of the exploration objective, like locally on the scale of like, say, a few seconds, changes in the environment probably aren't that important, because you're not really expecting, unless you have people or other objects that you're trying to track, like you're not expecting the environment to change over the course of 10 seconds or a minute. Now, a common, like you might have like a rock fall or like a door closes, and that typically affects planning. And one of the things that we would see happen is like you maintain a graph that represents the environment, and you get to an edge that was traversable, but now like the door closed. And they had scenarios like that in the finals. I'm not sure if we encountered any serious issues there, but one of the things we ran into with our field tests was if we didn't have a mechanism to update an edge, a robot would just wait at a location forever and maybe like walk back and forth because it thought that it could go in one direction and get home to return to communication, say. But it turned out that a door or such and such were closed and it couldn't go that way and it wasn't smart enough to go somewhere else. So even not necessarily like having some like high level reasoning about dynamics isn't always that important. It's just being able to respond to some changes. I guess from the perspective of exploration objectives, that's kind of a higher level thing also where maybe you have to have some understanding of like, this part of the environment changed, I need to map it again.
Yeah, that was...
which would be a really hard thing to incorporate, but maybe with an appropriate learning component, you could recognize like there have been changes to an environment or changes happen so often. Actually, one of the PhD students from my former group at CMU, Derek Mitchell, did a thesis on basically exactly this topic. He tried to track locations where there would be rapid changes in an environment and then maintain a model where like, well, I don't think the buildings are going to change that often, but maybe the parts of the environment where with like people walking around or cars moving back and forth, those change regularly, so I need to map them more often. And then also like going back to like this search and rescue scenarios, like maybe you want to maintain a map of an environment that represents the updates like movements in the rubble and so on. And you could either map it on a day-to-day basis, or maybe you have some knowledge of where things are changing, you map those in more detail. And I guess ultimately it depends a lot on the application domain and what you want to capture in the dynamics, whether it's people or a changing environment and so on.
Okay, thank you. Thank you, Micah, for your answer. I can see that Felipe has a question. Felipe, go ahead.
Hi, Micah. Thank you for your talk. Your work is really interesting and relevant, I think.
I hope.
So if I understood correctly, your work, the robots of your work, they collaborate, but it seems to me it's kind of a distributed collaboration, or robots are, their subtasks are independent, right? So my question is, how much more complex do you think it will be to create teams of robots? It can be drones or whatever, where they need to perform more elements within the same subtask, let's say.
Elements as in like more complex tasks locally, or?
Yeah, like instead of having distributed parts of the whole task where one robot does one thing and the others do something else, where they need to do like the same parts of the task together.
Okay, yeah. Thanks. There's a few elements of that I can answer. Another very good question. So first, do you remember that video I showed in the presentation of the Gaussian mixture model in red? The robots were exploring like a warehouse environment. So what I didn't mention on this time through the talk is those robots weren't using any interesting distributed planning, and they were still performing fairly well. And that was just because they had a shared model of the environment. So one of the things that frustrates me a bit in exploration problems is that I've been studying these problems for a long while, but they don't actually need a lot of explicit coordination, as you kind of hinted at right there. And actually, it's been one of my biggest challenges in getting results for like distributed planning because you actually don't necessarily always see a lot of variation in performance once you implement your fancy planner with suboptimality guarantees. Because just having an understanding of like what other robots have explored and what the map looks like provides you enough information to generally deconflict robots if you have those updates quickly enough and are also not in like a super narrow environment where your robots are always getting into conflicts between each other. And so for example, if you have two robots that are nearby each other exploring an environment, even if they're not making explicit plans about where one robot should go or the other should go, one robot may find that there's a lot of information off to the right and it'll go exploring that way. And as soon as it starts going that way, the other robot will see, well, there's other goals to the left that aren't already taken, and those are easier to reach, and I'll go that way. And then they just go in other directions. And the coordination ends up being more important only when the robots are forced to be near each other persistently. So that goes to the issue of other tasks and more nuanced problems. So one example that I'm interested in, I talked about target tracking briefly, and target tracking is interesting, has a little more persistent dynamics. The targets are moving around, and in that case, the robots have to coordinate a little more, and we see more interesting variations in performance because there's a lot more local interaction. And depending on the dynamics of the target tracking tasks, that could be more or less extreme. There's also another paper from a few years ago by Brian Williams at Virginia Tech that really excited me on, or actually a few papers, I think, on like task assignment problems using similar structure, like the submodular maximization techniques that I use in my own work in modeling like these task assignment problems that have interactions between agents. That paper focused on like task assignment to maintain connectivity, but there are other types of tasks that you can use a similar model. And that also potentially produces like interesting reward functions that require more explicit coordination, but also use similar techniques.
Thank you.
Yeah, thank you.
Thank you, Felipe, for your question. Is there any other question?
Yeah, I was wondering if you could talk more about the relationship between the first half and the second half. Like, did you, for the second half for the DARPA challenge, did you train on simulations, and what were the challenges of transferring from simulation to the real world?
So we did have simulations. I focused mostly on the drones, and we would develop in simulation a bit, and we're able to do single and multi-robot simulations with our multi-robot team. Although like simulations are easy when you have a small software stack, simulations are much harder when you have like a very large stack that's basically designed to take up a compute node on each of the individual robots. So it was a little harder. And what we'd actually do, especially like during more in the midst of the pandemic, when we weren't doing field testing, we did like games, like simulated games on a like monthly basis or so. And instead of field tests, we would run those games in simulation because in my work previously, like I could run a simulation on an exploration task, and that was enough. But for the Subterranean challenge, you also have to worry about like the operator interaction. Are you scoring artifacts? Your vision system working? There's a huge depth of all of these subsystems. And I think that generally a good amount of that transferred, but for the most part, all of our systems were based more on extensive field testing than learning from simulations. So we spent like a lot of time running our robots in limestone mines, or a limestone mine, in urban environment, a few caves as well, throughout the like past like 6 or 8 months. And that's what that was the biggest thing for us. It's a lot of work to get like 6 robots to run reliably. Like you can imagine if one robot has like a 10% chance of failing, then that becomes like a very, very high probability that one of your robots will have issues when you're trying to deploy them. So like getting to a point where we actually were able to fairly reliably deploy all our robots took a lot of time, especially since our hardware was being developed in parallel with our software. And I think I mentioned we didn't have a whole lot of like explicit coordination. So we would, various components used machine learning, like our terrain classification, artifact detection, but that was all fairly localized. And we used what are now like pretty standard techniques for like coverage planning and other elements of our planning stack. And those were basically tuned to like, well, what do we need to make this work in a larger environment, in a smaller environment? And we would do that by regularly testing in like larger spaces or then sometimes a little more narrow spaces. But what we didn't really plan for was that like in the competition environment, you went through like a narrow corridor to start, and then all of our options were just narrow spaces, and there weren't really any wider spaces to send our robots off into. Like one of the challenges that we hadn't really considered was like, we planned for our drones to fly in like wider spaces, and we just didn't have that option. You went down the corridor and there were a bunch of narrow doorways that we could barely even fit through. Some of the teams were able to deal with that because they had marsupial robots, so they could carry the robot into a narrower area. Or if they did a really good job in planning, like CMU was able to go through doorways sometimes, which is a really, really challenging task for a large drone because you have very little clearance. But even they like struggled like navigating the hallways. I think there were some videos of that. So yeah, a little bit of learning, and a lot of experience in field testing robots.
Oh, thanks.
Thank you, Stephen. And unfortunately, we're running out of time. But I would like to thank once again Micah for the presentation, for all the insights that he gave us. Both his work and on the DARPA challenge, and it was a pleasure having you here. I just would like to keep you 2 more seconds of your time so that we can announce the next speaker, which, okay. So our next section of Talking Robotics will be as usual in 2 weeks. And we're going to have Marinel Vasquez. She's an assistant professor at Yale Computer Science Division, and she will be talking about challenges and opportunities of data-driven human-robot interaction. So if you are interested in that topic, you should not miss it. And having said that, we would like to thank our sponsors, Animatas, and see you next session.